Welcome to your simple science summary of FS Physics. Today we're tackling topic 4, mechanics, a really core part of your IEB Further Studies Physics course. It's foundational stuff, isn't it? Designed to stretch you, get you thinking, and definitely gear you up for university physics.
Absolutely. Mechanics is, well, it's all about understanding why things move the way they do, or why they stay put. We're talking forces, motion, equilibrium. Think about the curve of a cricket ball, or how a satellite stays up there. Even that feeling when a car turns sharply.
Right, that feeling.
Yeah. So today we'll break down 5 key areas. Projectile motion, then uniform circular motion, gravitational fields, followed by orbits and satellites, and finally, torque and static equilibrium. The idea is to see how they all connect, why they're useful, and hopefully trigger some of those aha moments.
Fantastic. Let's dive in and unpack all of that for you. Okay, first up, projectile motion. This is like anything flying through the air just under gravity's influence, right? Like throwing a ball or maybe a drop from a plane.
Exactly. A package dropped, a ball thrown, even a long jumper. The key is that gravity is the only significant force acting once it's moving, ignoring air resistance for now. And this section really builds on kinematics, but we have to be super clear on vectors versus scalars first.
Ah, yes. Position, displacement, velocity, acceleration. Those are vectors. They have direction.
Correct. And distance, speed, just magnitude, so they're scalars. A common slip-up is thinking acceleration always points the way something's moving.
But it doesn't, does it?
No. Acceleration tells you the direction of the net force. If you're speeding up, okay, velocity and acceleration are aligned. But if you're slowing down, like applying brakes...
Then acceleration is opposite to velocity.
Right, precisely. And that's vital for projectiles.
So what about when things move in 2 dimensions, like firing a cannonball or that frog jumping you mentioned? How does gravity pulling downwards affect the sideways motion?
Okay, this is one of the coolest parts, and it feels a bit weird at first. For 2D motion, we can treat the horizontal and vertical components of the motion completely independently.
Independently, really?
Yes, completely. Vertically, the object is constantly accelerating downwards at about 9.81 meters per second squared, thanks to gravity. But horizontally, assuming no air resistance, there's no horizontal force. So, no horizontal acceleration.
Meaning its horizontal speed just stays constant.
Yeah.
The whole time.
Exactly. So that package dropped from a plane, it keeps moving forward horizontally at the plane's speed, even as it falls straight down towards the ground below.
Wow. Okay. My brain wants to fight that, but it makes sense if the forces are independent.
It does, and it explains that classic physics problem. A bullet fired horizontally and one dropped from the same height hit the ground at the same time.
Ah, because their vertical motion is identical.
Perfect. And for solving problems, this independence is gold. Choose positive directions, say up and right, and apply your kinematic equations separately to the x and y dimensions. Couple of key points. At the very peak of its vertical path, the vertical velocity is momentarily 0, and there's time symmetry. Time up equals time down to the same height. And the speed at a certain height going up is the same magnitude as the speed at that height coming down, just, opposite direction.
Okay, and you mentioned range. For athletes, long jumpers, shot putters, maybe even kicking a rugby ball.
Yeah.
What's the magic angle for maximum distance? Is it really 45 degrees?
It is for launch and landing at the same height. Our source confirms 45 degrees gives the maximum horizontal range. It's a balance, really. You need enough height to stay airborne for a good time, but also enough initial horizontal speed. 45 degrees hits that sweet spot.
Useful for sports, definitely.
That
Okay, moving from flying objects to things going, well, round and round. Uniform circular motion. We've done lines and curves, now circles.
Right, and this is everywhere. Wheels, planets, electrons around a nucleus, centrifuges. Newton's first law is key again.
Yeah.
Objects want to go straight. So if something is moving in a circle, there must be a net force pulling it off that straight path.
Always a force involved.
Always. In uniform circular motion, the object moves at a constant speed around a circle. We need some new terms here. First, period, t, time for one full circle in seconds. Second, frequency f, circles per second in hertz. They're just inverses.
Okay.
Then, angular displacement, theta, the angle swept out. We use radians here, not degrees. Remember, 2 pi radians is a full circle, 360 degrees. Radians make the math much cleaner.
Radians. Got it.
And finally, angular velocity, omega. How fast the angle changes in radians per second.
So how does this angular velocity connect to the speed we feel, like on a spinning ride at a theme park?
Good question. The connection is simple. Linear speed, or tangential speed, equals angular velocity times the radius, v equals or. That means points further out from the center have to move faster to cover more distance in the same amount of time.
Like on a merry-go-round. The horses on the outside are really moving, but near the middle it's much slower.
Exactly that. Same angular velocity, different tangential speeds.
What about direction, clockwise, anti-clockwise?
Yeah.
That depends where you're looking from, doesn't it?
It does. Which is why we define the direction of angular velocity using the right-hand rule. Curl the fingers of your right hand in the direction of rotation.
And your thumb points in the direction of the angular velocity vector, along the axis of rotation.
You've got it. And the linear velocity. Always tangent to the circle, changing direction constantly.
Now, here's something that always felt tricky. If the speed is constant, how can there be acceleration?
The classic question. Remember, acceleration is the rate of change of velocity. And velocity is a vector. It has magnitude and direction.
So even if the speed isn't changing,
The direction is changing constantly. Every instant, the velocity vector points differently as it follows the circle. That change is acceleration. We call it centripetal acceleration. And it always points towards the center of the
towards the
velocity.
center. Okay.
And Newton's second law, FMO, tells us if there's acceleration, there must be a net force causing it, pointing in the same direction. That force is the centripetal force, also towards the center. Crucially, it's not some new magical force. It's the resultant or net force that's already there, causing the circular motion.
So for a car turning,
It's friction between the tires and the road, pointing inwards for a satellite.
gravity.
Exactly, gravity pulling it towards Earth.
But what about that feeling of being pushed outward, centrifugal force? It feels incredibly real in a sharp turn.
It does feel real, but it's what we call a fictitious or inertial force. There isn't actually a force pushing you outwards.
So what is happening?
It's your inertia. Your body wants to keep going in a straight line, Newton's first law. The car turns under you, and the car door, or the seat, pushes inwards on you, providing the centripetal force to make you turn.
So the outward feeling is just my body resisting the inward push
Yeah,
because I'm in the accelerating car frame.
precisely. You're in a non-inertial reference frame. An observer outside the car would just see the car pushing you inwards. Centrifuges use this inertial effect. Denser stuff resists turning more, effectively moving outwards relative to the less dense stuff.
Okay, let's zoom out. From turning cars to the cosmos. Gravitational fields. We feel gravity all the time, but it's supposed to be the weakest force.
It is fundamentally the weakest of the four forces, but its reach is infinite, and it acts on mass, so over large scales it dominates. It holds planets, stars, galaxies together. It all starts with Newton's universal law of gravitation. Every mass attracts every other mass. The force depends on the product of the masses, and, crucially, the inverse square of the distance between their centers.
So this pen is pulling on me right now, minutely.
Yep, and you're pulling on it. But the gravitational constant g in the equation is tiny, so the force is negligible unless at least one mass is huge, like Earth. To make things conceptually easier, we talk about gravitational fields.
Right, fields. Like magnetic field, but for gravity.
Kind of. A gravitational field is the region of space around a mass where another mass would experience a force. We define the field strength, often written as g, as the force per unit mass. What's neat is the field strength at a point depends only on the mass creating the field and the distance from it. You don't need a test mass there to calculate it.
So Earth creates a field around it, and anything in that field feels a force.
Exactly. And near Earth's surface, that field strength is pretty uniform, about 9.81 newtons per kilogram, or 9.81 meters per second squared downwards. That's our familiar acceleration due to gravity.
Thinking about Earth's gravity leads us straight to orbits and satellites. Newton had that cool thought experiment, didn't he? With a cannon on a mountain.
He did. A brilliant visualization. Imagine firing a cannonball horizontally from a super high mountain. A slow shot falls to Earth quickly. A faster shot goes further. Fire it fast enough, Newton realized, and as it falls, the Earth's surface curves away beneath it at the same rate. It keeps falling, but never gets closer to the ground. It's in orbit.
So orbiting is just constantly falling but missing.
That's a great way to put it. Continuous falling under gravity. And gravity provides the centripetal force needed to keep the satellite, or the moon, or a planet in its curved path.
And this is where Kepler's laws come in, describing how these orbits actually work.
Yes. Johannes Kepler, using Tycho Brahe's incredibly detailed observations, no telescopes yet, remember, figured out 3 laws of planetary motion. First law. Orbits aren't perfect circles. They're ellipses, with the central body, like the sun, at one focus of the ellipse.
Meaning the distance changes.
Right. There's a closest point, perihelion, for the sun, and a farthest point, aphelion. Second law. The law of equal areas. A line joining the planet to the sun sweeps out equal areas in equal times.
Which means,
It means the planet moves faster when it's closer to the sun and slower when it's further away. Earth is actually moving fastest in its orbit around January.
never knew that.
Third law, the law of harmonies. This connects the orbital period, T, and the average radius, R. It states that the square of the period is proportional to the cube of the average radius, T or R. For everything orbiting the same central body, the ratio TR is constant. This lets us calculate orbital speeds, which depend only on the mass of the central body and the distance, not the satellite's mass.
So thinking about satellites,
Yeah.
what about those geostationary ones? The ones used for TV broadcasting, like DSTV here in South Africa. They seem to just hang there.
Geostationary satellites are a perfect application of these principles. They orbit Earth directly above the equator at a very specific altitude, about 35,786 kilometers up. At that height, their orbital period is exactly 24 hours, matching Earth's rotation. So from our perspective on the ground, they appear stationary in the sky.
Making them perfect for beaming signals to fixed satellite dishes.
Exactly. Communication, weather forecasting.
And
But because they all need that specific equatorial orbit at that specific altitude, it's getting crowded up there. Orbital slots are limited, and managing radio frequencies is a challenge.
Okay, last unit. Torque and static equilibrium. We've mostly treated things as points, but real objects have size, and where you push them matters.
Oh, it's absolutely crucial. Think about opening a heavy door. Do you push near the hinges?
No way. You push on the handle, far away.
Exactly, because you instinctively know that gives you more turning effect. That turning effect is torque. Torque, or the moment of a force, depends on the size of the force, the distance from the pivot point, we call this the moment arm, and the angle between the force and the lever.
You get the most torque when you push perpendicular to the door, right?
Precisely. Maximum torque happens when the force is perpendicular to the moment arm. The unit is Newton meters. Importantly, that's not Joule's torque isn't energy, it's a rotational push. And it has direction clockwise or anti-clockwise, also found using a variation of the right-hand rule.
And where does weight fit in? Does an object's weight just pull down from everywhere?
For calculations, we simplify. Every object has a center of gravity. It's the single point where we can consider the object's entire weight to act. For uniform, symmetrical objects, a ruler, a brick, is usually the geometric center. For odd shapes, you can find it by hanging the object from different points. The center of gravity is where the suspension lines cross. It makes torque calculations much easier.
So putting it all together, what does it take for something to be perfectly still, not moving, not rotating, static equilibrium?
Two conditions must be met simultaneously for static equilibrium. First, translational equilibrium. The net force acting on the object must be zero. All the pushes and pulls in every direction must cancel out. Sum of forces equals zero.
So no acceleration.
Right. Second, rotational equilibrium. The net torque acting on the object must be zero. All the clockwise turning effects must exactly balance all the anti-clockwise turning effects. Sum of torques equals zero.
No spinning or tipping over.
Correct. Think of a seesaw balanced perfectly, or a bridge supporting cars, or a construction crane lifting a heavy load without falling. It needs a big counterweight to ensure the net torque is zero.
And choosing the pivot point smartly can make solving problems easier.
Definitely. If you choose a pivot point where an unknown force acts, that force creates zero torque about that pivot, since its moment arm is zero, simplifying your equations. So you see how it all connects, from the arc of a ball to planets swinging around the sun to just making sure a bookshelf doesn't tip over. It's all mechanics.
It really is. Understanding these fundamental principles, forces, motion, energy, equilibrium, fields, rotation, it's not just about the exam, is it?
Not at all. It's about building a deep understanding of how the physical world works. It's the bedrock for so much engineering, technology, and further scientific study.
A foundation that really sets you up for tackling more complex problems later on.
Exactly. And the key is often breaking complex things down into these simpler components we've discussed. Keep asking why. Keep looking for those connections.
Well, you've been listening to your Simple Science summary of FS Physics. We hope this look at mechanics has clarified things and maybe even sparked some new questions for you. With this foundation, what physical puzzle will you try to unravel next?